I need to,
Oh, screen share.
if people come up,
You don't have, I mean,
with them.
you don't have to
during
pay
it.
attention too much. So if you're gonna stand over there, use one of these,
Okay,
Okay.
I'll sit here
Okay.
to play.
because the microphone's like right there. It's like if it's that, actually, oh, no, I don't know. It's up in there
gotcha.
somewhere. Because when we were testing it, we put it-
Where's a good spot to put it? I mean,
I don't know. Yeah, that's fine.
Melanie, did you share this?
No, I didn't.
Okay.
Oh, no, that battery's going. Sorry. I just put new ones in there. Press. Oh, press. I just put the battery. Sucking down the batteries like nothing.
This one. Hang over here too.
Yeah, I mean, I got mine. You got this, so,
Okay, gotcha. Yeah, we'll leave the battery.
There you go. Screen now. Press. Press. There you go.
I just like put it in my pocket. Cool. My phone's back.
Make sure you see your screen.
Yeah, okay. Should
Yeah,
I?
you can just, we're good, so just don't worry about it.
Okay. Sounds good. And then you hit the recording, correct? Okay, thank you. I think it's 9 o'clock. Should we begin? Okay, got it.
Well, good morning, everybody. Hope everybody's doing okay. We are Pathways to Safe Engineering, working with MT Facilities Management on a pathway project. Before we get into introducing ourselves and what we're doing, just wanted to give a recognition to our sponsors, which is Jake and MT Facilities Management, as well as our advisors being Dr. Watkins, State, as well as us.
Hi, everyone. I'm Maureen Henenfent.
I'm Jamel Thompson. Here's a presentation outline of what we're going to talk about, generally our background and scope of our project, the existing conditions of our design site, as well as stormwater management research is what went into picking our final design, all of our design, cost and scheduling, and some general recommendations we got for our project. So first things first, talking about our project scope. So our project in particular, we're tasked to design a pedestrian pathway that connects from Cliff Drive to Phoenix Drive, so connecting lower to mid campus, as well as being able to be followed by a bobcat. There are 3 teams working on this project in tandem with us. One team dedicated to the design of the overall structure of the path, as well as retaining walls. Another team that is tasked with chemical excavation and general logistics of the project. And us specifically, we're tasked with developing stormwater management for pre and post construction. Some general things about our site, we have a general area of 2.76 acres, with an average slope at the site of 8.5%.
So the first thing we took a look at in our project was the existing conditions. And we started off with our underground utilities. During construction, we didn't want to hit anything underground, cause more of a ruckus. So as you can see, we color coded everything. We used our GIS elevations there. We compared everything to the digital elevation model that we're doing. And we found the coverage for most of these pipes. We got our sanitary sewers about 20 feet underground, and our shallowest is the easternmost steam tunnel, which is currently active at 13 feet. We don't believe any of this will get in the way of our construction of this.
So before the Dow Environmental Sciences and Engineering building was constructed, an engineering firm was hired to do a soil analysis of the area, which is within or right near our project area. So we looked at borings 1, 2, and 4 and found that the soil consists of coarse fine sand to medium gravel. We also did an analysis on the USGS Web Soil Survey website, and it was determined there that all of the soil within the project area is classified in the hydrologic group of type A. What this means is that the soil on our site is very well drained and it's not very susceptible to erosion. However, it is highly acidic and does have sulfate in it, which can corrode concrete relatively quickly. Because of this, it is our recommendation that the pathway be constructed out of material other than concrete, like asphalt.
So before we go into our general design, we did research to figure out what is it that we actually want to do for design and think some certain check boxes that we want to do for our project. Within our research for stormwater management, we mainly use this low impact development manual for Michigan, LID for short. And this manual was very useful for our project, had a ton of different information that was specific to Michigan that really helped us with our site specifically. And then the general focus of low impact development is that we're trying to prevent flooding in our site, at our site, as well as protecting the stream channels of the natural flowing of water, improving and protecting the overall stormwater quality, as well as creating an opportunity for groundwater recharge. And some key determinants that we have to look at, and which is specific to our project, is making sure that we have a design that works in very cold climates, that looking at our geology and soil, which we just talked about, soil type A, thinking about the surrounding water bodies that are in our site. So for us, it would be the Portage Canal, as well as plant resources that are available to us, which we'll talk about later. So when we're breaking up and figuring out what we wanted to do is for our best management practices for this, it's broken up into two different components. We have non-structural best management practice and structural. So we're non-structural, we're thinking about specific ways to focus on stormwater management, and we wanted to minimize or remediate any of the total amount of disturbed area that we're going to be investing with this project, as well as allowing for infiltration of the groundwater by preventing as many impervious surfaces as we can in this design. We want to make sure that we are maintaining a low amount of total suspended solids, which is TSS, that is flowing through the stormwater in our project, as well as we want to make sure we're protecting the natural flow of the water, the steep slope of the site, as well as the soil. So now moving on to structural best management practice, we use, in picking our actual hydraulic structure, we use the, from the manual that we saw before, we use the structural management practice summary matrix that helped us figure out what we wanted to do. And some key determinants we looked at is being able to manipulate the stormwater runoff volume, as well as infiltration and overall quality, water quality. And we want to make sure our design can handle the design discharge controls for it, being able to help aid in the treatment of TSS, and as well as has a low maintenance requirement throughout the longevity of being constructed, as well as being able to, like I said before, works really good in a cold climate.
So our overall design can be depicted here, and something that our design centers around is a primary swale, which will be placed above the pathway. This will be a cobbled swale to withstand our steep slope, and it will catch all of the runoff coming from above the path. To deal with the runoff that actually comes from the path itself, we're choosing to put in a rolled curb made of asphalt on the lower edge of the path to collect that. If need be, we've also designed a secondary cobbled swale to go below the path if additional runoff needs to be collected. This will also be a cobbled swale and will just be a little bit smaller than our primary swale. Our primary swale will also be divided by 8 different detention basins shown here, and these will help promote infiltration and slow down the velocity of the water. They will be spaced 100 feet apart, and there will be a cleaning pond at the bottom.
Focusing on our primary swale now, when we were getting into our design of this, work for our drainage, we started off by thinking we wanted something vegetative so we could enhance water quality of the site and also help water infiltration. But we found with the slope of the site we were not figure that out. So we reduced to 3 options of paved swale, paved and concrete or asphalt, or we could go hollow swale, which with this option is still be infiltration. So this is what we chose. We had to design the size of the riprap, so we wanted to keep it stable with high flow, which I've experienced in the largest one of them. So we used hydration mesh and found that it turned out to be about 9 inches. So we're calling for the average diameter 12 inches. The classic riprap calls for anyway. We next chose geotextile filter fabric, which is a good medium in between the soil and the riprap. To help any scouring that existing conditions soil allow. Getting into the the sizing of this channel. We started off with our hydrology, post-development flow. This we used the 10-year return period, an duration storm for the area, and there we found an the rational method, given our smaller watershed area. That's how we got our flow rate. The mains end is the value from the roughness of the riprap itself. We have our project slope, and we have the side slope as well from the end out slope on the main as well. From there, we can calculate swale depth, and our top width is important for the soil cuts and fills. And then the overall layout of the cover, I want to go to and you don't want to take up too much space and have to create too many trees. So, and lastly, you want to stay under 10% of their velocity. It's also important to note that in our final design, we have about a foot extra depth just for an extra safety factor that end up with. And there are possibilities of greater floods, storm events. So we want to account for everything with this primary swale. A secondary swale can be considered. We're planning on that being a scale down for primary swale.
So like I mentioned before, our primary swale will be divided up by 8 detention basins. 2 are shown in this drawing here. Something that's important to note are the pollutants that will be coming off in the runoff, specifically TSS. Now, most of the pollutants are contained in what's called the first flush volume, which is the first inch of runoff. So our detention basins needed to account for the entire volume of this first flush. We calculated the first flush volume using the MDOT drainage manual with the equation shown here, where we divided our area by 12 and got a volume of 833 cubic feet. Each of our detention basins can hold 113 cubic feet of water, and there are 8 of them, so this will account for our first flush volume.
Now taking a look at our smaller method drainage, we have our whole curve. This is specifically meant for just the runoff coming to the path. So it's a much smaller area to account for than the primary swales, therefore smaller. But at the same time, nothing can show through pavement, so have a lot more runoff coming from that one area. And our goal here is in between, cooperation with the other groups. We have 2 retaining walls that we want to go in between, and we don't want to offset their project as much. So our goal is to keep this as small as possible. So what we did is we tried to minimize our maintenance end value, so minimize the roughness of the water and flow out as smooth as possible. So therefore, we chose a paved swale, so it makes sense to just match the same substance of the path itself. So we chose asphalt, and going through the same process for designing in with our hydrology for 10 years, 60 minutes. And the rational method, we found 0.33 feet per second of flowing with one foot. Our maintenance end as the asphalt, and the slope of the swale matches that of the primary swale. Bigger side slopes as well, pretty shallow. We don't want the pedestrian stepping in there. So we found our curve depth to be about 3 inches or so, so pretty small. It should be able to account for quite a bit of water. Our top width is minimal as well, and our velocity is still under that 10%.
So like I said before, we wanted to make sure we're protecting the soil, so we did some things that help with soil erosion control. That's broken up into 2 major parts, which is during construction and after construction. So for during construction, we have silk fences and sandbags that will be at the inlet and outlet of the of our soil, as well as around the whole entire construction site. And that's to help really just treat TSS while during the construction phase and making sure not too much water is coming into the site or not too much water is coming out of the site, as well as mulch blankets over the slope of the construction site, just another aid to protect that soil that's on the steep slope that we're constructing up there. As well as after construction, we have a revegetation plan, which we talked about in a moment, as well as the geotextile fabric that will be in the soil to kind of protect the soil that's right underneath our soil, so we're not damaging it too much, as well as having straw wattles placed within the soil. So if you're not familiar with that, straw wattles are compressed straws that is used to intercept infrastructure as well. That's used to intercept water, as well as requires little to no maintenance. That's all once you place it into where you're putting it at, and requires minimal funding. It also helps to collect the sediments that are running through the soil, as well as provide nutrients to vegetation growth throughout the duration of the life cycle of this piece of construction.
So because some area will need to be cleared for the path, we did develop a revegetation plan for after the path is constructed. The trees in our project area right now are mainly Norway maples, which are actually invasive to Michigan. So instead of those, we chose balsam firs to replant in the area. Balsam firs can thrive in the acidity of our soil. They can withstand the really cold temperatures of the Keweenaw, and they're good at slope stability. Very similarly, we also chose to put in maidenhair ferns in this area. They also can survive in acidic soil and do help stabilize the slope. In between these pieces of vegetation, we would like to put in a native seed mixture to help the biodiversity and the ecosystem of our project area.
Now, after all this designing, we conducted a outbound analysis to pretty much account for where is this water going after we design and place the structure at our site. So there's moving in two locations, and the first is going to be the water will move to a stormwater inlet that you can see up on the screen in the red circles. Those are places upon Community Drive. And then the second location is in the Portage Lake through the natural sloping of the area, as well as some outlets that goes right into the port.
All right, getting into cost and duration of this project. So to figure out the overall cost for our portion of the project, we used the MDOT weighted unit average spreadsheet from 2020. The 2020 version was a little bit more complete for what we were looking for, but we did scale up for the 2-year inflation. It was found that our most expensive item will be the riprap, which will cost about $47,300. In total, our portion of the project will cost $122,000. Something that's very important to note is, again, that this is just the environmental and stormwater analysis done by PTS engineering. So this does not include any of the work done by the other 2 engineering groups, and it doesn't include the actual construction of the pathway.
Yeah, this is just the stormwater portion of the project. Our schedule ends up being quite straightforward, actually. And when creating the schedule, we used RSM, which is a nationally recognized website or tool, aid construction. And what we did is we found our unit labor hours, or labor hours per unit, and we found the number of units for each bid and multiply it through to get this simple number of hours for each task. And we found that our longest duration to anyone's plan is going to be our channel excavation of the script. It's very detailed work we're doing, and it's doing that very cool then go for the extensive. And there are 4 major components of these activities that we carry out during construction. And upon further analysis, they're pretty simple actually. We lump them all together, and back to back to back. And biggest challenge is just lumping in other schedules. So ours are pretty simple. It's doing 8-hour work days, 5-day work weeks. And so we got a total of 25 days, which is 5 weeks for our portion of the plan.
So at the end, we combine the totals with the other engineering groups, and depending on what design is selected, we have different amounts that the project will cost. If Jabber Geotechnical's design is chosen to be used, the project in its entirety will cost $3,025,000. If Joe Engineering's designs are selected, the project will cost roughly $1,843,000. With both these projects combined with our drainage work, it'll take about 4 months for completion, and that is from when the paperwork is initially started to have been filled out all the way to the end of the revegetation plan.
Overall, with our design, we do have some recommendations that we wanted to take into consideration for the future of this project. We've alluded throughout the whole presentation that there should be a secondary swale placed on the northern side of the path, just to make sure that we're not overloading the primary swale and making sure that we're accounting for some more drainage that could be happening in that area. Being able to specifically tap into a storm sewer and not just hoping that it falls through, just like we talked about in that analysis. Drainage guards, moving them instead of on the outside of storm drains, moving them on the inside, just to prevent from them not tampering with or anything like that, as well as investigating other alternative options beside the path. So you can see in this next slide here, Princess Point just went through its own trucking site of making its own pathway to get to the park point. And these are wooden frame stairs with gravel inside, and that really helps with providing a lot more infiltration into the groundwater table. And just thinking about, even though their project scope is different, others we have a similar site area, as well as similar soil layout. So this is another alternative that besides. And with that, thank you all for coming. If you have any questions, you guys.
I was wondering about the operations for the construction of the project. Correct. So what about, you guys have any idea about any maintenance in the future that might be needed to be done to this project, or how often that will happen? Yeah, just how often, well, how long is the project going to be in quote unquote top shape before these maintenance? Sorry.
Okay, thank you. It's a great question. The question was, how long will the project be in good shape before any maintenance might be done to the project? Swales typically last about 25 years, and they can be maintained as well. Something I did not mention is a minimum of 2 feet per second of velocity. The swales is considered self. Not necessarily meet those, but our assumptions. But anyway, its maintenance should be minimal, and we assume issues like this would those options available. It would be minimal, so stuff out of there. Yeah, design so that sedimentation is minimalized, so that may be the only major maintenance that occurred. So, thank you.
But that's also not accounting for any other accidents or things that happen. And once like the structure settles, you could get some cracking within like the asphalt or things like that, and water seeping into areas where it shouldn't be, and that causes a lot of problems. So it definitely like in like the first couple of years of the project, of the structure being designed, those things look at, so making sure that the structure isn't even.
Oh, you were explaining, how you found out the soil was acidic.
Yeah, so one of the things that, or like I mentioned before, we use the USGS Web Soil Survey, which I'll just explain it for anybody who doesn't know. It's actually a really cool program. You can kind of select the area of soil you want to look at anywhere in the world, and it will tell you exactly some components of the soil, if it's good for construction, how the drainage is, stuff like that. So something that's in our soil is it's highly sulfuric, and that is known, any type of salt will corrode concrete a little bit faster. So that's how we came to that conclusion.
Related to the maintenance question, and maybe the other teams address this, but what happens in the winter is they want to be able to plow this path, right?
Yeah, they want to just have a path that is driven straight down the pathway. So I believe that the path was designed to be 12 feet wide, so that it can get down there. But once again, that wasn't the scope of my project, but that is something that I remember from other.
That was one of the reasons too why initially when the 3 teams got together, we wanted to do a little bit more of a straightforward path from the Dow building to the Great Lakes Research Center, or at least a switchback. But that made it complicated with having the width and the slope that it would be able to be plowed on. So that's kind of why our path ended up 800 feet long, stretching the length of the hill.
Yes, I'm just wondering about, the piles of snow on the side of the path. And I always think about this stuff at SDC, when you see giant piles and they start melting in the spring. I don't know the way that account for that in stormwater calculations. That's one other thing to think about.
Yes,
Part of the maintenance.
definitely.
Precipitation data, typically they come from stormwater runoff. You look at runoff numbers, it's area. Usually they come from that.
I think what you did is fine. You just try to still perfect sense for all of that.
Maybe further recommendation.
Let me stop the recording. Yeah, go ahead, just stop it. I'm trying to get it ready for